February 17, 2016. JAXA, the Japan Aerospace Exploration Agency, a satellite called Hitomi, lifts off from the Tanegashima Space Center. It is Japan's sixth X-ray astronomy observatory, and by far the most sophisticated. It has been in development for over a decade. It carries an instrument called the soft X-ray spectrometer, a microcalorimeter cooled to within 50 millikelvin of absolute zero, capable of measuring the temperature and motion of superheated gas across the universe with a precision that no other instrument in orbit had ever approached. By the technical consensus of the X-ray astronomy community worldwide, it was the most capable astrophysics instrument ever launched on a Japanese satellite. It cost approximately $286 million. It was a collaboration involving NASA, the European Space Agency, and the Canadian Space Agency. 38 days later, it was gone. Not destroyed by a launch failure, not lost to a collision, not the victim of a single dramatic external event. Hitomi was torn apart by a cascade of failures in its own attitude control system, a chain of software design flaws, operational errors, and at least one incorrect set of commands uploaded from the ground, compounded, according to some analyses, by a transient disruption to one of its sensors as it crossed a particular region of space above the South Atlantic Ocean. That region has a name, the South Atlantic Anomaly. And while the South Atlantic Anomaly did not, by itself, destroy Hitomi, the full story is more complicated and more interesting than that. The anomaly is a real and growing hazard to every satellite in low Earth orbit. It has caused documented failures throughout the space age. It is expanding, and the satellite industry is, right now, grappling with what that expansion means for the 10,000 spacecraft currently in orbit and the tens of thousands more being planned. This is the story of that region, what it actually is, what it actually does, and why the honest version, without the exaggeration, without the mystery mongering, is more important than any legend. Let me start by being clear about what the South Atlantic Anomaly is not. It is not a mystery. It is not supernatural. It is not the space equivalent of the Bermuda Triangle legend. The idea that ships and planes vanish in the North Atlantic for unexplained reasons. A story that has been thoroughly debunked by insurance statistics and weather records. There is no real Bermuda Triangle anomaly. The disappearance rate in that region is statistically indistinguishable from any comparable stretch of ocean. The South Atlantic Anomaly is something more straightforward, and in many ways more serious than any legend. It is a region above Earth where the planet's protective magnetic field is measurably weaker than anywhere else at comparable latitudes. In that region, the inner Van Allen radiation belt, a zone of high-energy, charged particles trapped by Earth's magnetic field, dips closer to the surface than anywhere else on the planet. It dips low enough to reach the operating altitudes of thousands of satellites, and the particles it brings with it are among the most damaging things in the near-Earth space environment. Every satellite in low Earth orbit crosses this region multiple times per day. Every crossing is a radiation exposure event, and the region has been getting larger and weaker for as long as we have been measuring it carefully. The title of this video says we don't know why satellites die there. That's the framing the story usually gets, but the honest truth is that we mostly do know why. The physics is well understood. What we are genuinely uncertain about is something more specific and more consequential. How fast the anomaly is growing, where it is heading, and whether the satellites being launched right now are designed for the radiation environment they will actually encounter over their operational lifetimes. This video is about the South Atlantic Anomaly. It is a region of unusually weak magnetic field stretching across the South Atlantic Ocean between South America and Southern Africa. In this region, Earth's protective magnetic shield. The force that normally deflects the charged particles streaming outward from the Sun and keeps the Van Allen radiation belts at safe altitudes above our satellites, dips close enough to the surface that the radiation belts dip with it. Every satellite in low Earth orbit crosses this region. Every crossing is a radiation exposure event. The SAA has been known since the early space age. It has been a recognized engineering challenge since the first satellites began experiencing unexplained glitches and anomalies above the South Atlantic in the 1960s and 70s. Satellite designers have been accounting for it, engineering around it, building safe mode protocols to survive it for 6 decades. What has changed is this: the European Space Agency's Swarm satellite constellation. 3 satellites that have been continuously monitoring Earth's magnetic field since 2013, has confirmed, in results published in late 2025, that the South Atlantic Anomaly has expanded by an area nearly half the size of continental Europe in just 11 years. Since 2020, a region southwest of Africa has been weakening faster than the rest of the anomaly, in a direction the standard models did not predict. At the same time, the number of satellites in low Earth orbit has grown dramatically, from roughly 2,000 in 2020 to approximately 10,000 by 2026. SpaceX alone has deployed more than 6,000 Starlink satellites in low Earth orbit. Amazon's Kuiper constellation, OneWeb. Multiple national programs, all of them crossing the South Atlantic Anomaly multiple times per day. The anomaly that every one of these spacecraft is passing through on each orbit is not the same anomaly the satellite industry built its engineering standards around. It is bigger. It is deeper. It is more complex, and it is changing faster than anyone predicted. By the end of this video, you will understand exactly what the South Atlantic Anomaly is and where it comes from. You will understand what it has done to specific satellites and missions throughout the space age, from Hubble's daily safe modes to the role it may have played in the loss of Hitomi. You will understand what the expansion means for the 10,000 satellites currently in orbit and the tens of thousands being planned. And you will understand why the honest version of this story, a story about the gap between what we built our technology to handle and what the planet is actually doing, is more important and more urgent than anything built around mystery or legend. So, what exactly is the South Atlantic Anomaly, and why does it exist? What actually happened to Hitomi, and what role did the anomaly really play? Why is every satellite in low Earth orbit, including the ones carrying your GPS signal, your weather forecast, and your internet connection, exposed to elevated radiation every single time it passes over that region? How has the SAA been expanding for decades, growing by half the size of a continent, without most people knowing it was happening? What does the most recent satellite monitoring data tell us about where the anomaly is going, and what does that mean for the mega constellations of 10,000, 50,000, potentially 100,000 satellites being planned for deployment in the next decade? This is not a video about the Bermuda Triangle. Let me be direct about this. The legend of the Bermuda Triangle has been thoroughly debunked. Multiple independent analyses have shown that the disappearance rate in the Bermuda Triangle region is not statistically different from the disappearance rate in any other comparable area of ocean. There is no anomaly. There is no mystery. The legend persists because humans are drawn to the idea of a place where normal rules do not apply, but the data does not support it. The South Atlantic Anomaly is different. It is real. The satellite failures it contributes to are documented, peer-reviewed, and acknowledged by every major space agency on Earth. The expansion of the anomaly is confirmed by 11 years of satellite monitoring data. This is a genuine, ongoing, and increasingly urgent engineering challenge facing the entire satellite industry. And the honest version of the story: told without the supernatural framing, and without the dismissive, "nothing to see here" a response, is more interesting, and more important, than any version built around legend. Stay with me, quick pause. If you're enjoying this kind of slow, careful storytelling, hit subscribe. Galaxy Pulse goes deep on stories others rush through. Now, back to the South Atlantic Anomaly. To understand why the South Atlantic Anomaly threatens satellites, we need to understand two things. First, what the region actually is, not a myth, not a mystery, but a specific physical feature of Earth's magnetic field, with a specific physical cause, 3,000 kilometers beneath the surface of the ocean. And second, what it means to operate a satellite in a radiation environment. What happens at the level of individual transistors and memory cells when a high-energy particle passes through, why some failures are temporary and some are permanent, and why the engineers who design satellites for low Earth orbit have been thinking very carefully about this particular region of space for 60 years. Let us start with the physics. Because once you understand what the South Atlantic Anomaly actually is, everything that follows, the satellite failures, the expanding boundary, the mega constellation challenge, will make a different kind of sense. In 1958, an American physicist named James Van Allen flew a radiation detector on one of the first American satellites, Explorer 1, and discovered something that nobody had known was there. The discovery itself is a small piece of space history worth telling. Explorer 1 was the United States' first successful satellite, launched in the aftermath of the Soviet Union's Sputnik. Van Allen, a physicist at the University of Iowa, had designed a compact cosmic ray detector to fly aboard it. When the data came back, it showed something strange. At certain points in the orbit, the detector's count rate dropped to 0. This was initially baffling. A detector designed to count radiation should not suddenly count nothing. The resolution turned out to be the opposite of what the 0 reading suggested. The detector was not seeing too little radiation. It was being saturated by too much. The radiation levels in certain regions of the orbit were so high that the detector was overwhelmed and stopped registering distinct counts. Van Allen had stumbled onto vast zones of trapped radiation that no one had predicted, surrounding Earth, in two broad donut-shaped zones extending from a few hundred kilometers to tens of thousands of kilometers above the surface, were vast populations of high-energy charged particles, protons and electrons, trapped by Earth's magnetic field and spiraling continuously along the field lines. Van Allen had discovered what we now call the Van Allen radiation belts, and the discovery fundamentally changed how engineers thought about sending anything into space. The mechanism that traps these particles is elegant. Earth's magnetic field forms closed loops, emerging from near the south magnetic pole and curving around to re-enter near the north magnetic pole. A charged particle moving through this field does not travel in a straight line. The magnetic force causes it to spiral along the field lines, and as it approaches the regions near the poles where the field lines converge and strengthen, it is reflected back, bouncing between the northern and southern hemispheres, over and over, sometimes for years. The particles are, in effect, trapped in a magnetic bottle, held in place by the geometry of Earth's field. The inner belt sits roughly between 1,000 and 12,000 kilometers altitude. It contains primarily protons, some of them with energies of hundreds of megaelectronvolts, moving at a significant fraction of the speed of light. These protons are produced when cosmic rays, high-energy particles from outside the solar system, collide with atoms in the upper atmosphere, producing secondary particle showers that inject protons into the belt. The inner belt is relatively stable, its population slowly replenished and slowly decaying. The outer belt, from about 13,000 to 60,000 kilometers altitude, is dominated by electrons. It is more dynamic than the inner belt. Its population surges and drops in response to solar activity, swelling during geomagnetic storms and contracting during quiet periods. Between the two belts is a gap, the slot region, where the fields of both belts are relatively weak. Most operational satellites in what we call low Earth orbit. The regime from about 200 to 2,000 kilometers altitude, where the International Space Station, most Earth observation satellites, most commercial communications constellations, and Hubble operate, sit well below the inner Van Allen belt. In theory, the Van Allen belts are not uniform. The inner belt does not sit at the same altitude everywhere above Earth's surface. Its lower boundary, the altitude at which the belt's population of trapped particles becomes significant, varies with latitude and with the strength of the magnetic field below. Where the magnetic field is strong, the belt is pushed higher. Where the field is weak, the belt dips lower. Over most of Earth's surface, the magnetic field is strong enough that the inner Van Allen belt remains safely above the operating altitudes of LEO satellites. Over the South Atlantic, it is not. The magnetic field over the South Atlantic is measurably weaker than anywhere else at comparable latitudes. This is a consequence of the same deep core dynamics that drive the broader weakening of Earth's magnetic field. A reversed polarity patch near the core-mantle boundary beneath this region, creating a local cancellation of the global dipole. The result, projected upward to the surface and into space, is a region of abnormally weak field stretching across the South Atlantic from roughly the eastern coast of South America to the southwestern coast of Africa. It is worth understanding where this weakness actually comes from, because it connects the satellite engineering story to the deep physics of our planet. Earth's magnetic field is generated by the geodynamo, the churning motion of liquid iron in the outer core, roughly 3,000 kilometers beneath the surface. This motion generates electrical currents, which generate the magnetic field. But the field the geodynamo produces is not a perfectly smooth dipole, like the field of a simple bar magnet. It is complex and lumpy, with regions of stronger and weaker field, and even small patches where the field direction is locally reversed relative to the global pattern. Beneath the South Atlantic, there is one such reversed polarity patch. In this region, the field generated by the core points in roughly the opposite direction to the dominant global field. Where the two overlap, they partially cancel. The net result, measured at the surface and in the space above it, is a zone of significantly weakened field, the surface signature of a specific structure in the flow of liquid iron deep inside the planet. This is the same physics that drives the migration of the magnetic North Pole toward Siberia. The same physics that has produced the roughly 9% weakening of Earth's overall field over the past 2 centuries, and the same physics that, on geological timescales, governs the major reorganizations and reversals that the field has undergone hundreds of times in Earth's history. The South Atlantic Anomaly is not a separate phenomenon from the broader changes in Earth's magnetic field. It is one of the most consequential surface expressions of those changes. Consequential, precisely because it sits directly above the orbital paths of thousands of satellites. In this region, the inner Van Allen belt dips, not by a small amount. The inner belt's lower boundary, which sits safely at altitudes of 1,000 kilometers or more over most of the planet, descends to altitudes of 200 to 800 kilometers over the South Atlantic, directly into the operating range of low Earth orbit satellites, and the particles that come with it are among the most damaging things in the near-Earth space environment. Consider this for a moment. The International Space Station orbits at approximately 420 kilometers altitude. Its crew members are shielded from most space radiation by the station's structure, the water in the walls of some modules, and the design of the sleeping quarters, which are positioned to provide additional protection. When the ISS passes over the South Atlantic Anomaly, which it does multiple times per day, given its orbital inclination, the crew receives elevated radiation exposure. NASA tracks cumulative dose for each astronaut. Spacewalks are scheduled around the SAA when possible. The radiation management protocols for the ISS are, in significant part, an ongoing accommodation to the anomaly's existence. This is not a hypothetical concern. It is an operational reality that NASA, Roscosmos, and their international partners manage every single day of every human spaceflight mission in low Earth orbit. The numbers make it concrete. Radiation dose aboard the ISS is measured continuously, and the data consistently shows that the South Atlantic Anomaly is responsible for a large share of the total dose. The crew and the station's electronics receive. During the portions of the orbit that cross the anomaly, the measured dose rate inside the station rises sharply compared to the rest of the orbit. The station crosses the anomaly on several of its roughly 16 daily orbits, and those crossings dominate the daily radiation accounting. This is why spacewalk scheduling takes the anomaly into account. When astronauts are outside the station, they have far less shielding than they do inside the pressurized modules. Conducting a spacewalk during an SAA crossing would mean accepting a higher radiation dose during the most vulnerable phase of the activity. Where the timing allows, mission planners schedule the most exposed portions of spacewalks to avoid the anomaly crossings. The station's sensitive equipment is also affected. Certain scientific instruments and computer systems aboard the ISS are known to experience elevated rates of single-event upsets during anomaly crossings. Some equipment is powered down or placed in protected modes during these crossings, much as Hubble protects its instruments. The anomaly is, in effect, woven into the daily operational rhythm of the most expensive structure humans have ever built in space. And if it affects human missions that extensively, consider what it does to uncrewed satellites, machines that spend their entire operational lives in that environment, with no crew to monitor their health, crossing the anomaly over and over and over again, for years. Under normal conditions, meaning anywhere outside the South Atlantic Anomaly, here is what a satellite at 500 kilometers altitude should experience. A relatively predictable, relatively stable radiation environment. The Van Allen belts are safely above. The atmosphere below provides modest additional shielding against lower energy particles. The satellite's electronics, designed to specific radiation tolerance specifications, accumulate radiation damage at a rate consistent with their design lifetime. A satellite designed for a 10-year operational life will, over 10 years in a normal LEO orbit, accumulate a total radiation dose within its design margins. What happens when that same satellite crosses the South Atlantic is different in kind, not just in degree. The particle flux increases dramatically. High-energy protons, the particles most capable of penetrating satellite shielding and reaching the sensitive electronics inside, are present at levels orders of magnitude higher than in comparable orbits elsewhere. A satellite at 600 kilometers altitude in a normal LEO orbit might encounter a relatively modest proton fluence. This same satellite crossing the heart of the South Atlantic Anomaly can encounter a fluence hundreds to thousands of times higher during that portion of its orbit. The radiation dose accumulated during SAA crossings is, for most LEO satellites, the dominant contribution to their total lifetime radiation exposure. A satellite that makes 15 orbital passes per day might spend 2 to 3 of those passes crossing the South Atlantic Anomaly. In terms of radiation dose, those 2 to 3 passes can account for the majority of the day's total accumulated dose. The consequences range across a spectrum. At the mild end, single-event upsets, individual memory cells flipping from 0 to 1 or back, causing data errors that the satellite's error detection systems can correct. Annoying, requiring additional computational overhead to manage, but not dangerous. In the middle of the spectrum, instrument upsets, where the anomaly triggers safe mode transitions, shutting down science instruments and requiring ground commands to restart. These are lost science time. For an observatory with a mission lifetime of 5 years, hundreds of instrument towers lost to SAA safe modes add up to a meaningful reduction in scientific output. At the severe end, cumulative damage to solar cells, reducing power generation capacity over the satellite's lifetime, degradation of detector sensitivity in science instruments, permanent damage to critical electronics components, shortening the satellite's operational life below its design specification, and, at the rare, catastrophic end, a single event upset in exactly the wrong place, at exactly the wrong moment, triggering a cascade that the satellite's other systems are not able to arrest. This is, possibly, part of what happened to Hitomi, though as we will see, the Hitomi story is more complicated than a single particle, and the anomaly was at most one link in a long chain of failures, most of which were on the ground. The story of how the South Atlantic Anomaly became a recognized engineering problem begins, as many space-age engineering stories do, with satellites that started behaving in ways nobody expected. The 1960s were the early years of the satellite era. The Van Allen belts had been discovered, their general structure was understood. Engineers were learning, through experience, what it meant to operate electronic systems in space, in vacuum, in temperature extremes, in the radiation environment that existed above the atmosphere. The South Atlantic Anomaly was not mapped in detail from the beginning. Its existence was inferred from the magnetic field measurements of the era, and from the first theoretical models of how the inner Van Allen belt would respond to the field's regional variations. But the practical impact of the anomaly on satellite operations was discovered the way many engineering problems are discovered, by having satellites behave unexpectedly in ways that, when tracked carefully, correlated with a specific geographic region. By the early 1970s, enough spacecraft had reported anomalous behavior above the South Atlantic that the anomaly was recognized as a distinct operational challenge. NASA documented it formally. Satellite designers began incorporating SAA radiation exposure into their lifetime calculations. Operations teams began developing protocols for managing the anomaly's effects on specific instruments. The Hubble Space Telescope, launched in 1990 into an orbit at approximately 540 kilometers altitude, became one of the most carefully monitored cases of SAA management in the history of the satellite program. Hubble's orbit takes it through the South Atlantic Anomaly on multiple passes per day. From the earliest days of the mission, the telescope's science instruments have been programmed to enter a protected mode during SAA crossings, shutting down the most sensitive electronics, saving any data in volatile memory to more robust storage, and waiting out the crossing before resuming normal operations. The Hubble operations team tracks exactly how much science time is lost to these safe mode events over the course of Hubble's 30-plus-year operational lifetime. The cumulative lost time amounts to a significant fraction of its total available observing time. Hubble has produced an extraordinary scientific legacy, more papers cited than almost any other astronomical instrument in history, and has done so while absorbing a continuous, daily, years-long bombardment of radiation from a zone of space that its designers knew would be there and tried, with careful engineering, to minimize the impact of. There is a nice piece of history here. The European Space Agency once produced an episode of its Hubblecast video series titled Hubble and the Bermuda Triangle of Space, referring directly to the South Atlantic Anomaly. The Bermuda Triangle of space framing has been around for years. But the people who actually operate Hubble do not treat the anomaly as a mystery. They treat it as a daily, well-understood engineering constraint that they have built their entire observing schedule around. The Space Shuttle program had its own SAA story. NASA officially documented that laptop computers aboard shuttle flights, the standard laptops that crew members used for on-orbit work, experienced memory errors and unexpected resets when passing through the SAA. The phenomenon was reproducible, correlated with the crossing, and understood well enough that crews were briefed on it as a standard operational consideration. The Globalstar Satellite Network, a commercial satellite phone company that launched its original constellation in the late 1990s, provides one of the clearest case studies in long-term SAA damage accumulation. Globalstar's satellites operated in low Earth orbits with inclinations that took them repeatedly through the South Atlantic Anomaly. Over years of operation, the radiation damage accumulated. The specific systems affected included components whose radiation tolerance, it turned out, was not adequate for years of SAA exposure. By the mid-2000s, the degradation was affecting the performance of parts of the network. The company eventually had to undertake a major program to replace much of its constellation. The Globalstar case illustrates something specific about how cumulative radiation damage interacts with business reality. When the original constellation was designed in the 1990s, the radiation environment models in use were based on the best data available at the time. The satellites were built to those specifications, with the radiation tolerance margins that the standards of the era called for. They were not poorly engineered. They were engineered to the standards that existed. But the actual radiation dose they accumulated over years of repeated SAA crossings degraded certain components, particularly the amplifiers in the communication payload, faster than the design margins had anticipated. The degradation was gradual. It did not announce itself with a dramatic failure. It showed up slowly, as declining performance across the network, as customers experiencing reduced service quality, as the engineering team tracing the problem back to radiation-induced component aging. By the time the cause was fully understood, the only practical solution was to replace the constellation. This was an enormous financial undertaking for a company already operating under significant pressure from the broader collapse of the satellite phone market in the early 2000s. The second-generation constellation was designed with improved radiation tolerance, informed by the operational experience of the first. The Globalstar story is important because it illustrates a failure mode that is less dramatic than a single catastrophic event, but in many ways more representative of how the SAA usually does damage, not in a single dramatic moment. Through years of patient, accumulated, incremental harm that slowly erodes capability until the system fails to meet its operational requirements. It is also a cautionary tale that is directly relevant to the mega-constellation operators of today. The lesson of Globalstar is that radiation environment assumptions made at design time have real financial consequences years later, when the satellites are operating in the environment that actually exists rather than the environment that was modeled. If the SAA is expanding, and if satellites are being designed to models that underestimate the future anomaly, then the Globalstar pattern, gradual degradation, declining performance, expensive replacement, could repeat at a scale orders of magnitude larger than the original. The satellite industry has learned, over 60 years, to live with the anomaly. What it has not fully learned to live with is an anomaly that is growing. Let us slow down for a moment and make the physics here concrete. Because the entire story, the satellite failures, the accumulated degradation, the expanding boundary, rests on understanding what happens when a high-energy particle from the Van Allen belts passes through a piece of satellite electronics. Think of a modern computer memory chip. It contains billions of individual transistors, each one storing a single binary digit, a 0 or a 1. The transistor works by controlling the flow of electrons in a tiny piece of semiconductor material. When you store a 0, the transistor is in one state. When you store a 1, it is in another. The chip works because those states are stable, because the transistor holds its state until you deliberately change it. Now, imagine a proton moving at a significant fraction of the speed of light passing through that chip. As the proton travels through the semiconductor material, it interacts with atoms along its path. It knocks electrons out of their normal positions. It leaves behind a trail of ionized material, a thin corridor of electrical disturbance, lasting for a fraction of a nanosecond, right through the heart of the semiconductor. If that corridor happens to pass through the sensitive region of a transistor, the region where the difference between a 0 and a 1 is maintained by a very small number of carefully positioned electrons, the ionization can flip the state of the transistor. A 0 becomes a 1 becomes a 0. This is called a single event upset, or SU. The term single event captures something important about this kind of damage. It is not the gradual accumulation of harm over time. It is a discrete event, one particle, one moment, one flipped bit. A satellite can operate flawlessly for years and then experience a single event upset in the span of a nanosecond as one proton happens to pass through one sensitive location. The randomness is part of what makes these events difficult to fully engineer against. You cannot predict which bit will flip or when. You can only build systems robust enough to detect and correct the errors when they occur, or robust enough to survive the consequences if an error slips through. There are several categories of single-event effects, and they vary in severity. The mildest is the single-event upset proper, a simple bit flip that corrupts a piece of data. More serious is the single-event functional interrupt, where the upset disrupts the operation of a device badly enough that it needs to be reset. More serious still is the single-event latch-up, where the particle triggers a short-circuit-like condition that can, if not quickly interrupted, permanently damage the affected component through overheating. And in certain power electronics, there are single-event burnout and gate rupture effects that can destroy a component outright. In most orbits, far from the Van Allen belts, single-event effects are rare. These satellites' error detection and correction systems can handle them, checking data against redundant copies, flagging errors, correcting them, and continuing. The overhead is manageable. The impact on mission operations is small. In the South Atlantic Anomaly, single-event effects are not rare. The proton flux in the heart of the anomaly can be hundreds to thousands of times higher than in comparable orbits elsewhere. A satellite crossing the SAA encounters many high-energy protons that it would not encounter over any other region of Earth at the same altitude. Each one of those protons is a potential bit flip. Each bit flip is a potential data error. And in systems with complex software, attitude control computers, command and data handling units, power management systems, not every data error is caught and corrected before it causes a consequential action. There is a second, slower form of radiation damage that is equally important for understanding the SAA's long-term effects. Total ionizing dose, TID, is the cumulative energy deposited in a material by ionizing radiation over time. Unlike single-event upsets, which are discrete events with immediate effects, TID damage is gradual and permanent. High-energy protons passing through a semiconductor material displace atoms from their lattice positions, creating defects that permanently alter the material's electrical properties. Over years of radiation exposure, these defects accumulate. Transistors that once operated cleanly begin to show increased leakage current, reduced switching speed, and higher power consumption. Eventually, the accumulated damage pushes the device outside its functional specifications. For solar cells, the panels that convert sunlight into electricity aboard satellites, TID damage is particularly critical. The efficiency of a solar cell depends on the precise crystal structure of the semiconductor material. Atom displacements from proton radiation degrade that structure, permanently reducing efficiency. After years of SAA crossings, a satellite's solar panels generate measurably less power than they did when launched. For a spacecraft operating on tight power budgets, even a few % degradation can force operational compromises. These are not hypothetical effects. They are measured, documented, and factored into satellite design through a body of engineering standards that represents 60 years of accumulated learning about what the Van Allen belts and the South Atlantic Anomaly do to spacecraft. The problem is that those standards were written for an anomaly of a specific size and intensity, and the anomaly has been quietly growing beyond those specifications. Here is where the stakes start to rise in a way that goes beyond the history of individual satellite failures. The South Atlantic Anomaly has been a known, managed engineering challenge for 6 decades. Every major space agency, every serious satellite manufacturer, every experienced satellite operator knows about it. The engineering standards that govern how satellites are designed for low Earth orbit include margins for SAA radiation exposure. The operational protocols that govern how satellites are operated include procedures for managing SAA crossings. The system works imperfectly, at significant cost, with occasional dramatic failures, but it works. The global satellite fleet operates in the SAA every day, and most satellites complete their design lifetimes without catastrophic failure. What is changing is that the anomaly the global satellite fleet was designed to operate in is not the anomaly that fleet is currently operating in. The Swarm satellite constellation, ESA's 3-satellite magnetic field monitoring mission, operating since 2013, has been measuring the SAA with precision no previous instrument could match. The data it has returned over 11 years of continuous observation tells a story that the satellite industry cannot afford to ignore. The SAA has expanded by an area nearly half the size of continental Europe since 2014, about 2 million square miles. The core region of the anomaly, where proton fluxes are highest and radiation damage is most severe, has been drifting slowly westward and northward. And, since 2020, a region southwest of Africa has been weakening faster than the rest of the anomaly, developing in ways that the standard models built from 20th century data did not predict. The particle radiation environment that 10,000 satellites are crossing multiple times per day is measurably different from the environment those satellites were designed to handle. The question is not whether this is a problem, it is. The question is how serious a problem it is, and how quickly the satellite industry can adapt. Now, let us return to Hitomi, because the real story of what happened to Japan's most powerful X-ray observatory is more complicated and more instructive than the version that usually gets told. The popular framing is simple and dramatic. A single charged particle in the South Atlantic Anomaly flipped a single bit in Hitomi's computer, and the satellite tore itself apart. It is a clean, satisfying narrative, a particle, a bit, a cascade, a loss. It is also not what JAXA investigation actually concluded. The AstroH mission, Hitomi, had been in development at JAXA since the early 2000s. It was conceived as Japan's answer to a specific scientific challenge. X-ray astronomy had, by the 2000s, produced an extraordinary picture of the hot, energetic universe, galaxy clusters, black holes, supernova remnants, neutron stars, using telescopes like Chandra and XMM Newton. These telescopes were superb imagers. They could show you where the X-ray emission was coming from with extraordinary spatial resolution. What they could not do was tell you, with precision, how the hot gas responsible for that emission was actually moving. The soft X-ray spectrometer on Hitomi was designed to do exactly this: a microcalorimeter detector, an instrument that measures the tiny temperature rise produced when a single X-ray photon is absorbed, with a detector cooled to within 50 millikelvin of absolute zero to minimize thermal noise. Could measure the energy of each arriving X-ray photon with a precision thousands of times better than any conventional X-ray detector. That precision translated directly into precision in measuring the Doppler shift of emission lines, the slight change in photon energy produced when the emitting plasma is moving toward or away from the observer. With the soft X-ray spectrometer, astronomers could measure the velocity of hot gas in galaxy clusters to within tens of kilometers per second. The instrument had no peer. Nothing like it had ever been launched. Nothing remotely like it was planned for the near future. To understand why this instrument mattered so much, it helps to understand what X-ray astronomy is actually trying to see. Most of the ordinary matter in the universe, the matter made of protons and neutrons, the matter we are made of, does not sit in stars. It sits in vast clouds of hot, thin gas, particularly in the spaces between galaxies within galaxy clusters. This gas is heated to tens of millions of degrees, so hot that it glows in X-rays rather than visible light. Studying it requires X-ray telescopes above the atmosphere, because Earth's atmosphere absorbs X-rays before they reach the ground. For decades, X-ray telescopes could image this hot gas. They could show its distribution, its temperature, its overall structure. But imaging is not the same as measuring motion. To understand how a galaxy cluster formed, how it is evolving, whether the gas within it is turbulent or calm, whether it is settling or being stirred up by the activity of a central black hole, you need to measure how the gas is moving. And measuring motion requires spectroscopy of extraordinary precision. The ability to detect the tiny shifts in X-ray energy produced by gas moving toward or away from the observer. That is what Hitomi's soft X-ray spectrometer was built to do, and what no previous instrument could do well. It represented the culmination of decades of detector development. The microcalorimeter technology at its heart had been in development across multiple institutions, including significant contributions from NASA Goddard Space Flight Center. For years, a previous Japanese attempt to fly a similar instrument, aboard the Suzaku satellite in 2005, had failed when the instrument's cooling system malfunctioned shortly after launch. Before any science could be done, Hitomi was, in a sense, the second attempt to fly this revolutionary capability. Hitomi launched on February 17, 2016. It reached its planned orbit without incident. In the first weeks of the mission, the commissioning process began, turning on systems one by one, checking them out, calibrating them. The spacecraft systems were working. The instruments were coming online. The mission appeared to be proceeding nominally. On March 26, 2016, a series of events began that JAXA Accident Investigation Board would spend months reconstructing. The resulting report, a detailed, 90-page analysis, is one of the most thorough public accountings of a spacecraft failure ever produced. And what it describes is not a single cosmic particle. It is a chain of failures, most of them on the ground, in software, and in operations. Here is what actually happened, as best the investigation could reconstruct it. The satellite had just completed a maneuver to point at a distant active galaxy. After the maneuver, the attitude control system needed to determine the spacecraft's orientation and rotation rate. It relied on a combination of star trackers, cameras that identify star patterns to determine which way the spacecraft is pointing, and an inertial reference unit, which uses gyroscopes to measure rotation. The first problem was with the star trackers. They had a known issue, identified shortly after launch, where they would unexpectedly switch from tracking mode into acquisition mode, effectively losing their lock on the star field. Because of this known issue, the operations team had configured the system to rely more heavily on the gyroscopes during certain phases. The gyroscopes, however, were reporting a rotation that was not actually occurring. The attitude control system, receiving this false rotation data, concluded that the spacecraft was spinning when it was not. It commanded the reaction wheels, devices that control orientation by spinning internal flywheels, to counteract the phantom rotation. This produced a real rotation. The reaction wheels, spinning up to cancel a rotation that did not exist, induced an actual spin in the opposite direction. As the real rotation developed, the angular momentum built up in the reaction wheels. Normally, this momentum would be unloaded, bled off, by magnetic torquers, devices that push against Earth's magnetic field to manage the spacecraft's rotation. But the magnetic torquers did not unload the momentum effectively. The reaction wheels kept accumulating angular momentum, and the spin kept increasing. The spacecraft entered a safe hold mode, designed to stabilize it in emergencies. The safe hold mode fired the reaction control thrusters to try to stop the spin, and here is the fatal error. The thruster control parameters were wrong. On February 28, nearly a month before the failure, ground controllers had uploaded a new set of thruster control parameters to account for a change in the spacecraft's configuration after the deployment of its extensible optical bench, a 6-meter boom that held part of the X-ray instrumentation. The new parameters were incorrect. They did not properly account for the deployed configuration. The procedure for updating these parameters lacked adequate documentation and verification. The work had been delegated in a way that, according to the investigation, did not ensure the parameters were correct. When the safe hold thrusters fired using these incorrect parameters, they did not stop the spin, they accelerated it. The spacecraft spun faster and faster, at a high enough rotation rate, exceeding the design limits of the structure. The solar panel paddles and the extensible optical bench experienced forces they were not built to withstand. They broke off. Without solar power, the satellite lost the ability to generate electricity. Its systems shut down. The last telemetry was received on March 26. The U.S. Space Surveillance Network later tracked multiple pieces of debris from the satellite, the remains of the solar panels, and the optical bench. The JAXA accident investigation identified the root causes as a combination of factors. The star tracker issue, the false gyroscope reading, a single point of failure in the attitude control software design that allowed one faulty measurement to override all other systems, inadequate procedures for updating the thruster parameters, and the disabling of certain safety checks. Where does the South Atlantic Anomaly fit into this? The honest answer is, possibly at the very beginning, possibly not at all. Some analyses, including the summary in the technical literature, suggest that the anomaly may have transiently disrupted the star tracker as Hitomi crossed it, contributing to the initial loss of accurate attitude information. But the anomaly did not cause the gyroscope error, did not cause the reaction wheel spin up, and most importantly, did not cause the incorrect thruster parameters that turned a recoverable situation into a fatal one. Those were design and operational failures on the ground. So, the dramatic version of the story, a single cosmic particle destroyed a $300 million satellite, is, at best, a significant oversimplification. The SAA may have been one trigger among several. The actual cause of the loss was a cascade of human, software, and operational failures that the satellite's own design was not robust enough to arrest. This matters because it tells us something important about how spacecraft actually fail. They rarely fail from a single dramatic cause. They fail from chains, sequences of individually survivable problems that compound, in the absence of adequate safeguards, into catastrophe. The SAA is a real hazard, but blaming Hitomi entirely on the SAA lets the actual, fixable failures, the software design, the operational procedures, the verification gaps, off the hook. The scientific loss, regardless of cause, is difficult to overstate. In the brief period of science operations before the failure, the soft X-ray spectrometer had produced its first observations of the Perseus galaxy cluster, measuring the velocity of hot gas in the cluster with a precision never before achieved. Those observations were immediately recognized as a landmark result, providing direct measurement of the surprisingly quiet motion of gas within the cluster. The paper reporting these observations has been cited hundreds of times. The results shaped years of theoretical work on galaxy cluster physics. What the Perseus observation found was, in its own way, as surprising as the instrument was sophisticated. The hot gas in the Perseus cluster, which contains a large, active central galaxy with a supermassive black hole pumping energy into its surroundings, was expected to be quite turbulent, churned up by the black hole's activity. Instead, Hitomi found that the gas was moving relatively gently, with turbulent velocities much lower than many models had predicted. This had implications for how astronomers estimate the masses of galaxy clusters, which in turn has implications for using clusters to study the large-scale structure and evolution of the universe. 4 days of observation from a single instrument changed how an entire subfield thought about its measurements. And the instrument that produced them is gone, not because of a single particle, but because of a chain of failures that began on the ground. There is a coda to this story worth noting. The scientific community recognized that the capability Hitomi represented was too important to abandon. JAXA, with international partners including NASA, built a replacement mission, X-RISM, the X-ray imaging and spectroscopy mission, carrying an instrument very similar to Hitomi's soft X-ray spectrometer. X-RISM launched in 2023 and has been successfully operating since, finally delivering the kind of high-precision X-ray spectroscopy that Hitomi was designed to provide. The capability survived. The first attempt did not. The difference between the two, between a mission lost to a cascade of preventable errors and a mission that succeeded, lies almost entirely in the lessons learned from the Hitomi investigation about software design, operational procedures, and the management of single points of failure. The most representative story of what the SAA does to satellites is not Hitomi. It is the quiet, accumulated damage that unfolds over years, not days, the accumulated damage, the slow degradation, the gradual erosion of capability that no single event triggers but that accumulates, orbit by orbit, crossing by crossing, until a satellite that was designed to last 15 years fails at 12, or an instrument that was calibrated to a specific sensitivity has drifted beyond its recalibration range, or a solar panel that was generating 100 watts of power at the beginning of its life is generating significantly less at the end. These are the quiet failures of the SAA, less dramatic than a satellite spinning apart, more representative of how the anomaly actually affects the global satellite fleet. The Hubble Space Telescope provides the longest-running case study in SAA management. In more than 3 decades of operation, Hubble has completed hundreds of thousands of orbits, crossing the South Atlantic Anomaly on multiple passes each day. The telescope's science instruments have been through multiple generations of electronics, with astronauts servicing missions replacing components that had accumulated radiation damage with updated systems. The gyroscopes, the precision pointing instruments that allow Hubble to maintain its extraordinarily stable pointing during long exposures, have failed multiple times over the mission's history. While gyroscope failures have multiple causes, the radiation environment Hubble operates in, including the SAA, is part of the operational context the servicing missions were addressing. Even the Wide Field Camera 3, installed during the 2009 servicing mission and responsible for many of Hubble's most celebrated images in the years since, accumulates total ionizing dose at every SAA crossing. Its detectors show the characteristic dark current increase and charge transfer efficiency degradation that are the signatures of accumulated radiation damage in silicon. The telescope's operations team monitors these parameters continuously, adjusting observing strategies to maintain scientific quality as the detectors age. There is also a scientific flip side to the SAA worth mentioning. Some missions have deliberately measured the particle environment within the anomaly rather than just trying to survive it. The Pamela experiment, a particle physics detector launched in 2006 aboard a Russian satellite, studied cosmic rays and the near-Earth radiation environment, including measurements within the SAA. Its data confirmed theoretical models of the proton fluxes in the heart of the anomaly, and detected unexpectedly high levels of trapped antiprotons, particle-antiparticle pairs produced by cosmic ray interactions with the upper atmosphere, and trapped in the same magnetic structures that trap the protons. It was a genuine scientific discovery, made possible by an instrument willing to operate in the most challenging radiation environment in low Earth orbit. The anomaly is not only a source of damage, it is also a natural laboratory for studying particle physics in a regime that cannot be replicated on Earth. But for every satellite that benefits scientifically from SAA measurements, there are thousands that simply endure the damage and try to survive it. The satellite industry of 2026 looks nothing like the satellite industry of 2006. 2 decades ago, there were fewer than 1,000 operational satellites in Earth orbit. Most of them were in geostationary orbit, parked at nearly 36,000 kilometers altitude, where they hover over a fixed point on Earth's equator. A smaller number were in low Earth orbit, weather satellites, Earth observation satellites, military reconnaissance satellites, scientific missions, and the International Space Station. In 2026, there are approximately 10,000 operational satellites in orbit. The overwhelming majority of the new satellites are in low Earth orbit, and the majority of those are operated by a single company. SpaceX's Starlink constellation has grown from a concept in 2015 to more than 6,000 deployed satellites by 2026. Operating in orbital shells, primarily between 340 and 570 kilometers altitude, Starlink provides broadband internet service to millions of customers worldwide. Its satellites are the most numerous artificial objects ever placed in orbit around Earth. Every Starlink satellite crosses the South Atlantic Anomaly multiple times per day. SpaceX has not published detailed data about Starlink's SAA-related anomaly rates or the specific radiation tolerance specifications of Starlink's electronics. What is publicly known is that Starlink uses commercial off-the-shelf components rather than traditional radiation-hardened electronics, a deliberate design philosophy that trades radiation tolerance for lower cost, lighter mass, and access to the latest commercial electronics technology. The model works because the constellation is so large that the loss of individual satellites can be absorbed into the overall system. Redundancy. When a Starlink satellite fails early, it is deorbited and replaced with a new one. The question that the SAA expansion raises is whether that model, cheap satellites, high replacement rate, constellation-level redundancy, remains viable as the anomaly grows. If the average radiation lifetime of a Starlink satellite decreases because the SAA has expanded and deepened, the replacement rate increases. That is a significant operational cost increase. And the replacement satellites being built today are being built using SAA models that may already be underestimating the future radiation environment. Amazon's Project Kuiper, deploying its planned constellation of more than 3,000 satellites in LEO, faces similar considerations. OneWeb, owned by Eutelsat, has deployed several hundred satellites in polar LEO orbits that cross the SAA at high inclination. Multiple national government programs, from China's Guo-Wang constellation to the European Union's IRIS² program, are planning LEO broadband constellations that will add thousands more satellites to the same orbital regime. By 2030, if current plans proceed, there may be 50,000 to 100,000 satellites in low Earth orbit. All of them will cross the South Atlantic Anomaly. The aggregate radiation exposure of the global satellite fleet in the SAA will be larger than anything the space industry has previously managed. The consequences of this collision between an expanding anomaly and an expanding satellite fleet are beginning to appear in unexpected places. The satellite insurance market has been adapting. Underwriters who specialize in LEO satellite risk have updated their radiation environment models to reflect the swarm data. Premiums for LEO constellation satellites have been affected as the actuarial calculations have incorporated the expanding anomaly. The design standards bodies are in motion. The European Cooperation for Space Standardization and the International Organization for Standardization both publish the technical standards that satellite manufacturers worldwide use as the basis for radiation design specifications. These standards specify the radiation environments that satellites in different orbits should be designed to withstand, including the SAA contribution to total dose. These bodies periodically update their space environment standards to reflect the latest SAA models from missions like Swarm. The gap between when a satellite is designed and when it actually operates is typically 5 to 10 years for complex missions, or 2 to 3 years even for the faster-moving commercial operators. A satellite being designed today, based on the current best estimates of the SAA, will be operating in the SAA of 2030 and beyond. The current best estimates of the SAA in 2030 are models, projections, not certainties. If the SAA continues expanding at its recent rate, those models may be underestimates. The specific challenge of the new, faster weakening region, southwest of Africa, deserves particular attention. The standard SAA models, built from decades of magnetic field observations and particle measurements, characterized the anomaly as a single, roughly oval weak zone centered over the South Atlantic. The swarm data from 2020 onward shows that this characterization is no longer adequate. The development of a region southwest of Africa that is weakening faster than the main SAA structure means that the geographic extent and the radiation intensity of the anomaly are both larger and more complex than the models that current satellite designs were based on. There are 3 ways to think about what the SAA expansion means for the future of space operations. They sit on a ladder, from the most conservative to the most challenging. Each one is held by serious people in the satellite industry and the space science community. Each one has real supporting evidence, and the choice between them will be made, ultimately, not by debate, but by data, by what the SAA does over the next decade as the monitoring networks watch and the mega-constellations operate. The conservative interpretation is that the SAA expansion is a manageable challenge and engineering will adapt. The satellite industry has been managing the SAA for 60 years. The expansion adds cost and complexity, but does not fundamentally change the character of the problem. The response is the same as it has always been. Update the radiation environment models, update the design standards, build satellites with appropriate margins for the new specifications, and accept that some satellites will fail earlier than planned and need to be replaced. This view is supported by the resilience of the satellite industry to date. Despite the SAA, despite every managed anomaly from every LEO satellite that has ever operated, the industry has grown. It works. The satellites that modern civilization depends on are in orbit and functioning. The engineering community has demonstrated, repeatedly, that it can adapt to the SAA's challenges. The weakness of this view is that it assumes the expansion will continue at a rate that remains within the adaptive capacity of the industry. The acceleration since 2020 and the development of the unpredicted faster weakening region southwest of Africa suggests that the anomaly's behavior may be less predictable than the conservative view assumes. The moderate interpretation is that the SAA expansion requires systematic, industry-wide design standard updates that have not yet been fully implemented. In this view, the critical issue is the lag between the science and the engineering. The swarm data is clear. The anomaly has expanded and is continuing to expand, with new structure developing that was not in the models. The satellite designs currently being finalized for deployment in the next 3 to 5 years are based on SAA specifications that may already be out of date. The design standard updates that the standards bodies are working on will take additional time to be finalized, adopted by manufacturers, and incorporated into spacecraft designs. During that lag, a significant number of satellites will be deployed that are underspecified for the radiation environment they will actually encounter. This view is supported by the documented timelines for standards updates and the lead times in satellite development. It does not predict catastrophe. It predicts that some percentage of satellites deployed in the next 5 years will have radiation lifetimes shorter than their design specifications, a real but bounded problem, one that the industry can manage if it moves with appropriate urgency. The bold interpretation is that the SAA expansion may reflect a broader, longer-term change in Earth's near-space radiation environment that the satellite industry is not yet equipped to handle. In this view, the expanding SAA is not just a localized engineering problem. It is one manifestation of a geomagnetic system that is reorganizing in ways we do not yet fully understand. The connection between the SAA and the broader weakening of Earth's magnetic field means that the long-term trajectory of the anomaly is linked to processes in Earth's core that operate on geological timescales. If the weakening continues, if the anomaly continues to expand, the radiation environment in low Earth orbit in 2040 or 2050 could be substantially more severe than it is today. This view does not predict a satellite apocalypse. Modern civilization's dependence on satellites will not simply end because the SAA is bigger, but it does suggest that the satellite industry needs to think about the long-term trajectory of the radiation environment, in the same way that coastal cities think about sea level rise, as a structural change in the operating environment that requires not just engineering adaptation, but a fundamental shift in how infrastructure is planned, designed, and financed. Here is what is worth saying before we leave the theoretical landscape. We built 10,000 satellites for a planet whose magnetic field we assumed was stable. Engineers calculated radiation lifetimes based on magnetic field models built from decades of historical data. Insurance underwriters priced satellite risk based on those same models. Mission planners scheduled replacement satellite deployments around the predicted lifetimes of the ones being replaced. The entire logistics infrastructure of the satellite industry was built on an assumption of a predictable radiation environment. The field was never perfectly stable. We just were not watching it carefully enough to know how much it was changing. The Swarm constellation, more than any other instrument in history, has given us the ability to watch. And what it has shown us, the expansion, the acceleration, the new faster weakening region, is a reminder that the stability we assumed was a temporary condition, not a permanent one. After everything we have seen, the Hitomi cascade, the global star degradation, the decade of swarm data, the mega constellation challenge, the three interpretations. The question is no longer whether the SAA is a serious problem for the satellite industry, but it is. The question is whether the industry is responding to the correct version of the problem, not the SAA of 2010, the one the current design standards were built for, but the SAA of 2026 and beyond. And here is where the story takes a turn that most coverage has never gotten to. Here is the strange thing about how the South Atlantic Anomaly has been covered in popular media. The story exists in two forms, and neither of them is quite right. The first form is the mystery framing, articles and videos about the Bermuda Triangle of space, focus on the legend, the sense that something supernatural is operating in this region. The SAA is invoked as a real-world counterpart to a debunked myth, a place where satellites mysteriously malfunction and die. The framing is entertaining, it generates clicks, and it fundamentally misrepresents what the SAA actually is, which is a well-understood physical phenomenon with a known cause, known effects, and known engineering responses. The mystery framing does a specific kind of damage. It makes the SAA sound exotic and rare, when in fact, every satellite in low Earth orbit crosses it every single day. It makes the failures sound random and inexplicable, when in fact they are documented, understood, and in most cases anticipated by the satellite designers. And it makes the situation sound stable, a fixed, known hazard, when in fact, the anomaly is expanding in ways the satellite industry is actively grappling with. The second form is the brief technical mention, articles about Earth's magnetic field, or the Van Allen belts, or satellite operations, occasionally include a paragraph about the SAA as a relevant complication. These mentions are more accurate, but they are usually too brief to convey the actual scale of the engineering challenge. Let me tell you specifically what the popular coverage has missed. The first thing it has missed is the actual cause of the Hitomi failure. The dramatic, single-particle version of the story is repeated widely, but the JAXA investigation's actual findings, the cascade of software design flaws, the incorrect thruster parameters, the operational failures on the ground, are rarely conveyed. The honest version of the Hitomi story is less dramatic, but far more useful, because it identifies failures that can actually be fixed. Blaming a satellite loss entirely on cosmic radiation suggests there was nothing anyone could have done. Identifying the real cascade of human and software failures suggests there was a great deal that could have been done differently. The second thing it has missed is the cumulative damage story. The slow degradation of satellites over years of SAA crossings, the Globalstar case, the gradual aging of Hubble's detectors, is less dramatic than a satellite spinning apart, but it is far more representative of how the anomaly actually affects the global fleet. This is the part of the story with the clearest lessons for the mega-constellation operators currently deploying thousands of satellites into the anomaly. The third thing it has missed is the late 2025 swarm result, the most comprehensive satellite-based measurement of the SAA ever published, confirming the expansion by half the size of Europe and identifying the new faster weakening region southwest of Africa. The specific finding about that new region, which is developing in ways the models did not predict, has been almost entirely absent from popular discussion. The fourth thing it has missed is the mega-constellation angle, the direct connection between the SAA's expansion and the deployment plans of SpaceX, Amazon, and others. The satellite industry's internal discussions about updating design standards, revising radiation lifetime projections, and incorporating expanded SAA models into new satellite designs are happening in technical working groups that popular science journalism does not typically cover. And there is a deeper connection that popular coverage treats as two separate topics when it is really one. The SAA is expanding because Earth's magnetic field is weakening in this region. The magnetic field is weakening because of processes in Earth's outer core. The same processes that are driving the magnetic North Pole toward Siberia, and that may, on geological timescales, reflect a field that is reorganizing in significant ways. The SAA story and the broader magnetic field story are the same story, viewed from different angles. The surface consequence of the deep Earth changes in near-Earth space is a radiation zone that is getting larger and more severe. In the period since the ESA swarm publication in late 2025, several parallel streams of research and operational response have been shifting the picture. The first development is in the monitoring network itself. ESA has indicated that the swarm constellation will continue operating into the late 2020s, with planning underway for successor missions to maintain the continuity of precision magnetic field monitoring into the 2030s. This scientific argument for continuity is precisely the situation we have been discussing. The SAA is developing new structure. The models need continuous updating, and losing the monitoring capability at a moment when the anomaly is in active development would be strategically counterproductive. The second development is in the satellite insurance market. Insurers who provide sophisticated risk analysis of satellite operations have been updating their space weather risk models to incorporate the latest SAA expansion data. The updated models show increased risk for LEO satellite constellations, particularly those operating in orbital inclinations and altitudes that maximize SAA crossing frequency. The third development is in the design standards process. The European Cooperation for Space Standardization has been updating its space environment standards, the technical documents that specify the radiation environments that satellites are required to be designed to withstand. NASA's space environment models, which characterize the inner and outer Van Allen belts, are similarly in continuous update cycles that incorporate new particle measurement data. The SAA's representation in these models is being updated to reflect its measured expansion. The fourth development is in operational space weather services. NOAA Space Weather Prediction Center provides real-time space weather information to satellite operators worldwide, including current assessments of the radiation environment in low Earth orbit. As these services incorporate updated SAA models, satellite operators are receiving radiation environment assessments that are based on more accurate, current models than those embedded in their satellites' original design specifications. This creates a kind of information asymmetry. The operators know, in near real time, that the SAA is larger and more intense than the satellite was designed for. The satellite's engineering margins were calculated for the old SAA. The satellite is operating in the new one, managing that asymmetry. Operating satellites in an environment that has evolved beyond their design specifications is the practical daily challenge that the expanded SAA has created. The next decade of space operations will be shaped by the intersection of two trends that are both accelerating. The first trend is the expansion of the satellite fleet. The deployment of mega-constellations in low Earth orbit is proceeding at a pace that would have seemed extraordinary a decade ago. Thousands of satellites are being launched every year. Every one of them will cross the South Atlantic Anomaly multiple times per day for its entire operational lifetime. The second trend is the expansion of the anomaly itself. The swarm data shows a consistent expansion over 11 years, with an acceleration since 2020, and the development of new structure that the models did not predict. Whether that expansion continues at its current rate, accelerates further, or eventually stabilizes is not yet known. But the direction of the trend is clear. The collision of these two trends, more satellites, larger anomaly, is the defining challenge for near-Earth space operations in the coming decade. The engineering response is already underway, and it is multi-layered. At the satellite design level, manufacturers are incorporating updated SAA models into their radiation tolerance calculations. At the operational level, satellite operators are developing more sophisticated SAA management protocols, using real-time particle flux monitoring to adjust instrument modes in response to the actual radiation environment rather than a static, pre-planned schedule. At the infrastructure planning level, the insurance industry and the standards bodies are creating the economic and regulatory framework that will drive satellite designs toward adequate radiation tolerance for the actual near-future SAA. The geomagnetic science connection adds a longer-term dimension. The SAA's expansion is driven by processes in Earth's outer core, specifically by the growth of the reversed polarity magnetic patch beneath the South Atlantic. Those processes operate on timescales of decades to centuries. The models that project the future evolution of the SAA are extrapolations of trends observed over a relatively short instrumental record. The honest assessment is that we do not know what the SAA will look like in 2040 or 2050. We know its current state with good precision. We know the direction of the trend. We know that the new, faster weakening region is developing, and that the acceleration since 2020 was not predicted by the models in use before 2020. But the geodynamo is a complex, non-linear system, and its behavior on decadal timescales is not predictable in detail. The prudent engineering response to this uncertainty is not to design for the worst conceivable scenario. That would be unaffordably expensive, but to build in adaptability. To design satellites with enough margin that moderate increases in the SAA beyond current projections can be absorbed. To maintain the monitoring infrastructure that allows the models to be updated as the actual anomaly evolves. And to build the regulatory and economic frameworks that can rapidly propagate updated specifications into new satellite designs as the environment changes. This is not a solved problem. It is a managed problem. The management is improving, but it requires sustained attention, sustained investment, and a public and regulatory environment that takes the SAA's expansion seriously. And here is what makes all of this truly remarkable. The South Atlantic Anomaly has been affecting satellites quietly for as long as satellites have existed. For 60 years, it has been the engineering challenge that every LEO satellite mission has had to plan for, budget for, design around. Thousands of engineers have spent careers learning its properties, quantifying its effects, building the shielding and the radiation-hardened components and the safe mode protocols that let satellites survive it. And through all of that, the global satellite fleet has grown, 10,000 satellites, a multi-billion-dollar annual industry. GPS guiding billions of smartphones to within a few meters, anywhere on Earth. Weather satellites issuing storm warnings that save tens of thousands of lives each year. Earth observation satellites tracking glaciers and forests and crop yields and sea levels. Satellite internet providing connectivity to hundreds of millions of people in regions where no cable or fiber infrastructure exists. All of it built and operated and depended upon in the shadow of a radiation zone that every single one of those satellites crosses multiple times per day. Let that sit for a moment. We built the infrastructure of modern civilization, the satellites that make the modern world work, to operate through a damaged region of Earth's protective shield. Not a perfect shield, not a shield we designed. The shield that Earth's geodynamo happens to have produced. With this anomaly in this location, expanding in this direction, for reasons that have to do with reversed polarity patches in the liquid iron of the outer core 3,000 kilometers below the ocean floor. And the satellites manage it, most of them, most of the time, with smart engineering and careful operations and a lot of redundancy. Now the shield is getting thinner in this region. The zone where it is thin enough to threaten satellites is getting bigger. And we are putting more satellites up there, not fewer, more than ever before in history, by orders of magnitude, with more coming every month. The answer to that combination of facts is not to stop. The global satellite fleet is too important to civilization to stop. The answer is engineering, careful, sustained, continuously updated engineering. Building systems that can adapt to a planet whose magnetic field is not the stable background condition we assumed it was. The field was never perfectly stable. We just were not watching it carefully enough to know. Now we are watching. The swarm constellation is measuring the anomaly's growth, orbit by orbit. The standards bodies are updating the specifications. The insurance market is pricing the risk. The engineers are designing the next generation of satellites with larger margins than the last. The South Atlantic Anomaly is growing. The satellite industry is adapting. The outcome of that race, between an expanding radiation zone and an industry adapting to it, is not yet determined. But it is being watched, carefully, by the right people, with the right instruments, and that, given what was happening without anyone watching closely enough, is the most important thing. But here is the thing about the South Atlantic Anomaly that most coverage never reaches. It is not the only radiation challenge in near-Earth space. There is another one, not caused by a magnetic anomaly, but by the transition region between the inner and outer Van Allen belts, in the medium Earth orbit where GPS satellites operate, and in the regions that crewed spacecraft must pass through on their way out to the Moon. A region where the radiation environment is highly variable, and where the next human missions beyond low Earth orbit will have to navigate carefully. The question of how to protect the electronics and the crews aboard spacecraft during transits through the Van Allen belts is one of the less discussed but more urgent engineering challenges in the current lunar exploration program. That is a story for next time. Tonight, we did not just learn about a dangerous zone of space above the South Atlantic. We watched what happens when the infrastructure of modern civilization is built to operate in a radiation environment that was assumed to be stable, and then, quietly, turns out not to be. We saw Hitomi, Japan's most sophisticated science satellite, over a decade in development, carrying an instrument that had no equal anywhere on Earth, destroyed 38 days after launch. Not, as the dramatic version claims, by a single cosmic particle, but by a cascade of software design flaws and operational errors that the satellite's own design could not arrest, possibly triggered in part by the anomaly's effect on a sensor, but fundamentally caused by failures on the ground. We saw the Globalstar network slowly degraded over years, its components eaten away orbit by proton radiation, until a major replacement program became the only option. We saw the Hubble Space Telescope entering safe mode every single time it crosses the South Atlantic, every day, multiple times a day, for more than 3 decades, because the alternative is to let the most important astronomical instrument ever built be damaged by radiation that its engineers knew would be there. And we saw, through 11 years of swarm satellite data, an anomaly that has grown by half the size of a continent and is developing new structure that the models did not predict. In the same decade that the number of satellites in that anomaly has grown from hundreds to 10,000 and is projected to grow to 50,000 or more. This is not a mystery. It is an engineering challenge, the most consequential engineering challenge in near-Earth space operations, and it is getting harder. Even now, with 60 years of data and 3 continuously orbiting magnetic field monitors, the picture is not complete. We do not know the long-term trajectory of the SAA expansion. The swarm data gives us 11 years of precise measurement. Extrapolating that data to 2030, 2040, and beyond requires models of the underlying geodynamo behavior that are not reliable on those timescales. We do not know what is specifically driving the new, faster weakening region southwest of Africa. The swarm data documents its development clearly. The deep core dynamics that caused it to develop independently of the main SAA structure are still being studied. We do not know whether the mega-constellation satellite designs currently being finalized will be adequately specified for the SAA they will actually encounter. The design standards updates are underway. They are not complete. Satellites being built now may be deployed into an anomaly larger than the one they were designed for, and we do not know whether the ISS crew radiation dose management protocols, developed for a specific SAA geometry, will need to be revised as the anomaly continues to evolve relative to the station's orbital path. These are open questions. The monitoring continues, the engineering adapts, the answers will come from data, not from models. There are a few things worth taking from this story that go beyond the South Atlantic Anomaly. The first is that spacecraft rarely fail from a single dramatic cause. They fail from chains, sequences of individually survivable problems that compound, in the absence of adequate safeguards, into catastrophe. The Hitomi loss is the clearest possible example. The popular story blames a cosmic particle. The actual story is a cascade of software, design, and operational failures. Understanding the difference matters, because the chain of failures version identifies things that can actually be fixed. The second is that cumulative damage is harder to manage than catastrophic failure. The dramatic failures get attention. The cumulative ones, slow degradation across many satellites over years, are in some ways more dangerous, because they erode capabilities slowly enough that they are easy to attribute to other causes and easy to defer responding to. The third is that the infrastructure of modern civilization is more geophysically dependent than most people appreciate. GPS, weather forecasting, global communications, financial transactions, all of these functions depend on satellites. Those satellites depend on operating in a specific radiation environment. That environment is part of Earth's geomagnetic system. The geomagnetic system is changing. The dependence runs all the way down. The fourth is that adaptation is not the same as solution. The satellite industry is adapting to the SAA. That adaptation is real, ongoing, and sophisticated, but it is adaptation to a moving target, an anomaly that is growing in ways the adaptation has to keep pace with. And the fifth is this: the swarm mission, 3 satellites, measuring Earth's magnetic field continuously for 11 years, has been one of the most consequential investments in planetary self-knowledge that any space program has made. Without it, we would not know the SAA had expanded by half the size of Europe. Without it, we would not know about the new, faster weakening region. The value of monitoring the planet carefully, with good instruments, continuously, is demonstrated clearly by what the monitoring has found. So I want to leave you with a few questions tonight. What does it mean to build the infrastructure of civilization, to operate within a natural system whose behavior you have been underestimating? How many other systems, Power grids, shipping routes, agricultural infrastructure are built on assumptions about natural stability that may not hold. When Hitomi was lost, was that a failure of engineering, of operations, of design standards, or of something more fundamental? A failure to build systems robust enough to survive the chains of small errors that complex machines inevitably produce? And what does it say about the relationship between human technology and the natural world that we have built a global satellite fleet of 10,000 spacecraft? And every single one of them crosses a radiation zone multiple times a day, and most of the people who depend on those satellites have never heard of it. Sit with those for a moment. They are bigger than the SAA. If this story stayed with you, tell me in the comments which moment was the one that pulled you in. Was it the real story of Hitomi, lost not to a single particle but to a cascade of failures on the ground? The Globalstar degradation, a commercial network slowly eaten by accumulated radiation. The swarm data, showing the anomaly growing by half the size of Europe in 11 years. Or the realization at the end that we have built the infrastructure of the modern world to operate inside a radiation zone that is expanding, and that the satellites being launched right now may not have been designed for the anomaly they will actually encounter. I want to know. And if you want more stories like this, real engineering consequences of real planetary science, told without the hype and without the dismissal, subscribe to Galaxy Pulse. We go beyond the headlines every single time. I will see you in the next one. 10,000 satellites circle Earth right now. Every day, each of them crosses a region of space where the shield is thin. Most of them survive it, some don't, and the region is growing. We built the infrastructure of the modern world to operate inside a weakened shield, and the weakening is not finished yet. It is, in a sense, just getting started.